The next person we're going to hear from is Lindsay Goodwin, and the presentation is Novel Methods for Characterizing Ionospheric Irregularities in the High-Latitude Ionosphere. And
should I do anything or just let the video play?
I gotcha, no worries.
Sweet, thank you. Hi everyone, and thank you for coming to my e-poster. Just to make things a little more streamlined, I decided to throw all my figures into slides. So today I'm going to be talking about irregularities in the high-latitude ionosphere and my research into them more recently. An irregularity is really just a fancy term for a plasma density structure, and it's important to understand where these come from and when, because they change radio wave propagation and over-the-horizon communication. The way that I'm looking at these structures is I'm creating these things called Irregularity Spectra, which is just a fancy way to organize our density structures with respect to their size. So one of the more well-known studies that did this was Kelly et al. In 1982. In this study, they used the Chattanooga Incoherent scatter radar featured here. An incoherent scatter radar, I might get yelled at for this, is really just a fancy, powerful radar that looks at the plasma properties in the ionosphere. It's way more complicated than that, but we don't need to go into that for this. And in the study, they took these meridional scans of plasma density, so this is the latitude and this is altitude, and they took a cut at 350 kilometers, took a Fourier transform, and then they created this spectrum here. And they saw that they had this little feature here, which was indicative of day-side energetic particles creating plasma density structures. But what was strange is that these are midnight observations. So from this, they could conclude that day-side energetic particles and precipitation could impact the entire high-latitude ionosphere. And even though the study is the bee's knees, we can improve upon it using newer techniques and newer instruments. So one of the issues is that this scan took about 12 minutes to take, just because they were using a steerable dish. And we know that the ionosphere changes a lot more quickly than that. As well, the study was limited to just looking at the auroral region, and we can improve upon that now as well. So one of the newer instruments that we have are called Advanced Modular Incoherent Scatter Radar, or AMISRs. And they have three identical ones sitting in the high latitude ionosphere. So here we have Pfizer, the Poker Flat Incoherent Scatter Radar. Here we have Riser N, which is the Resolute Bay Incoherent Scatter Radar North. And here we have Riser C, which is the Resolute Bay Incoherent Scatter Radar Canada. And these are their fields of view at different altitudes. But if we focus on a Riser N, this is a 25 beam mode that you can have from phasing these different antennae in and out of different radiation patterns. And what's important is that you can look at the plasma density along these different directions nearly simultaneously, meaning you can get a wider snapshot of what the ionosphere is doing than what Chattanooga could. However, the issue is you don't have the same spatial resolution. Even when you have modes that have more beams in this, you have a hard time getting this fine scale as Chattanooga could, which had a 10-kilometer resolution at 350 kilometers altitude. But we can cheat a little bit, and we can use physics to cheat. So this is a hypothetical experiment. Here I have Riser N, and here I have different beam modes. These orange squares are places where I could take measurements in this hypothetical situation. I should say that between 200 and 400 kilometers, we are restricted to have a range resolution of 24 kilometers, or between 200 and 400. But if I look at a specific altitude, so 350, for example, I have two measurements in this hypothetical experiment. And if I have some structure sitting here, I only have one measurement of the structure, so I'm not really getting a complete picture of what's going on here. And I can see smaller scale structures. But if we recall that we have a magnetic field in the high latitude ionosphere, and we recall that diffusion is the major transport mechanism along these field lines, we know that the irregularities that we have, the structures that we have and see at this region map up to here. As well, we have a good idea of where plasma is produced and how it recombines, and so we're able to map these measurements up to whatever altitude we want. So in this example, at 350 kilometers, we now have more measurements and we can get a better picture of what we have in our irregularities at different scale sizes. So if we apply this to one example, and this is just a preliminary thing, here I have plasma density from Riser N. they're all at the same azimuth, but different elevation angles. So that means that they're overlapping, but they're pointing at different angles upwards. This is all plasma density, and if I have one period, I have this one period here, where I have a slightly enhanced plasma density. If I take all these measurements and I map them to 350 and I make a spectrum out of that, and if I do the same thing in this relative depletion here, then I get the spectrum here. So I have a spectrum during a relatively enhanced plasma density and during a relatively depleted plasma density. The orange lines in both these cases are a fit to the entire spectrum. The red lines are a fit to the larger scale structures because this is spatial frequency, so it's kind of an inverted scale. And the green lines are a fit to the smaller scale structures. And what we can note is that the red lines are the same, but the green lines are a little different and it's steeper here. And so that would indicate that there's some physical process that's acting on these smaller scale structures that's changed between whether or not we had a depleted or an enhanced plasma. But this is a very preliminary study, and I want to apply it to different regions and times and all that good stuff to learn more about the ionosphere and our irregularities. And that's all I got. Thank you.
Right.
I hate the sound of my own voice, so that was torture, by the way.
I can sympathize.
I thought it sounded great, Lindsay.
But it sounded wonderful. It is very strange to listen to yourself give a video. But it was a fantastic presentation. Thank you so much. Do you have, does anybody have questions?
I have a question. This is N0AX. I noticed on your graph of the size of these various structures that you're interested in, some of them were pretty small pretty small is relative, but some of them were on the order of the size of wavelengths that hams have access to. And it's conceivable that we could excite these structures by lighting them up with energy near their spatially resonant frequency. And I was wondering if that would be of interest. Try sort of a modified radar kind of thing to transmit at a frequency that these things are resonant at. You'd get a much bigger, you'd either get a notch or a peak, I'll put it that way. And so, we could develop a program of either RBN or WSPR or some other ham protocol that could serve as sort of a horizontal sounder kind of thing to see when these things are out there.
Oh, I hadn't really thought about that. That's pretty, yeah, I would be interested in that. If I could talk to you more about that later, that would be...
Sure, just email me. We can figure out what's going on.
I'm very new to ham, so I don't know how the ham works. Sweet, thank you.
Okay.
And I think that's very similar to how SuperDarn senses things, because SuperDarn is HF, and it's going to be, it's a coherent scatter radar. So those it's going to scatter off of the field line irregularities that have a similar spatial scale to the wavelength of operation. So if you were, say, on the 20-meter band and you were, or on 14 megahertz, if your radar were operating on 14 megahertz or your ham radio were operating on 14 megahertz, you could get scatter conceivably from like the 14 irregularities that have spatial scales of about 14 meters. So I think that's a very similar case. Do you agree, Phil?
Yeah, I would agree. As Lindsay knows, anytime you're trying to scatter energy off of something, if you're picking out the Bragg condition, which is you've got things that are, say half the wavelength of the probing wave, you end up getting really bright scatter off of that. And so I think that was Ward's point, is that, if you've got tens of meters structures, okay, we have people on this call who have transmitters at tens of meters, all right? So honestly, you're then doing a radar experiment, and that coherent scatter is really, really bright. I mean, it like sometimes you have to turn down the knob on systems that we normally use, which are set to detect really weak things. So that's the thing to remember about this community, is that it's not just passive, it's active, is that people have the ability to actually ping things, and there's a reasonable spread of wavelengths, you know, in the hundreds of meters down to the few meters and lower than that, they're not continuous, but they're spread out. And if you can figure out what to illuminate with them within the license requirements that people have for the amateur band, you can do something interesting. So should work.
And HAMS, they talk about FAI type propagation modes, don't they?
Yeah, exactly. You know, in fact, you know, for people on the call, you know, a lot of these irregularities are so tightly aligned to the magnetic field, okay, because a lot of them have electrons involved because they're very light as the primary response when you hit it with something, and electrons really don't want to move off the field lines very much, and often when we see coherent kind of backscatter of the kind that's been referred to here, that was even mentioned in a previous talk. If you get more than literally a degree or two off looking perpendicular to the magnetic field, the signal drops like a stone. So that's why they're FAI, field aligned irregularities. And but the good news is that if you're hitting them pretty much perpendicular, they're really bright. So it's a good and a bad thing, but it's certainly accessible to people with moderate power levels of the kind that I think amateurs are able to do if you're located kind of in the right direction, because it depends on the magnetic field geometry where you are, because you're only going to get scatter from those places that are really perpendicular in most cases.
I think Anton has a question.
Or two.
Yeah, hi Lindsay, it's Anton. I have a few scientific questions to you about assumptions you made. So my questions would be, what's the model you are using for mapping, and how realistic it is, as we know how dynamic and irregular high latitude ionosphere is. So it's the first question. So second one is, you are looking at, according to what I see in your plots, at spatial scales, tens to hundreds of kilometers, that is MSTAD range. And again, we know that TAD wavefronts are tilted, and how do you account for that when you apply your mapping? And the last question is related to, we have a GNSS receiver scintillation monitor sitting in Resolute. Have you tried looking at GNSS and the spectrum of GNSS signals and trying to compare the spectral slopes?
Okay, so first question is, what model are you using?
Yes, exactly.
So I'm using IRI 2016. So that should take into account like the tilt of the magnetic field, for example, and our GRF as well. Your second question was, sorry.
Yeah, I think you'd like, okay, yeah, we can discuss it later. You know, IRI is not the best model to present high latitude ionosphere, first of all, and we have a better options for that.
Fair enough.
But thanks, I got your answer, yeah.
Yeah, and this is something I'm just starting as well. So yeah, there are some improvements. And your last question, I might have missed your middle question, but your
second question was related to, you're looking at MSTID's range, that is few tens of 200 of kilometers. And when you're applying your mapping, let's say from 200 kilometers, switching everything up to 350, you kind of have to account for that. Because if you have a irregularity having a tilted wavefront, so essentially you have an error when doing this mapping to a fixed height. That's what I mean.
Sure, but yeah, if we have an irregularity that's sitting in a magnetic field, we can assume that along a magnetic field line, that like if you see an enhancement, it maps in some way. So through like diffusion.
Yeah, well,
like,
like you are overlapping with a different. We're talking about different irregularities, like TIDs that are obviously present in high latitudes as well. But they do propagate horizontally, and they do have a tilted wavefront. But okay, we can discuss it again later. Just to something I'm just suggesting to think about that too. And my last question was about GNSS receiver, and if you have.
Yeah, I haven't gotten to that yet. Okay. So yeah, so the answer is no to that.
It would be a nice continuation of this work. We can discuss it too. Yeah, would be interested to see that.
About 3 minutes.
Sweet.
It looks like Gareth's hand is raised.
Cool, thank you.
Yeah. I just wanted to make a comment on that the last set of questions there. It's difficult. I think working on this project, Lindsay and I have been kind of struggling when we map up the irregularities. Is kind of what should we be mapping with? How should we map that plasma profile? And one of the things we kind of did the old knee-jerk reaction that everybody does in the community. It's like, oh, we can just use IRI to kind of guide us. But then, of course, in the polar cap, IRI is better than the vacuum, and that's about it. So, I mean, we're looking at other things in the fact that we have an incoherent scatter radar available to us, so we can actually get a good sense of maybe what the background looks like, and that's a good way to help it. But again, there's assumptions that we have to make in terms of how do we map it, and other things too, like assumptions that everything's quasi-static. There's no MSTIDs rolling through, and we have to account for hopefully we don't have Aurora roaring through and kind of throwing all of our assumptions out the door. So it's a dynamic region, of course. So
yeah, I think it's a good solution. One of the solutions to that, to compare your technique with something existing, it will be to look at GNSS data, the spectrum, and comparing at least spectral slope. I know these are a little bit different spatial scales, where when looking at GNSS, these are few hundreds of meters, but you are looking at a little bit higher up in size, but still, providing we have a power law, they should be at least comparable. And by the way, the numbers I see on your presentation are similar to what we see in GNSS data, and it would be nice really to compare them same time, same epochs.
I'd like that. Cool, thank you.
Wonderful. Any last questions for Lindsay and Gareth?
There's one, I think, question from John Armstrong that's in the chat. The first two lobes of structure remind me of multipath intensity plots. Any chance the dips are part of a multipath phenomena? I think that was to you. But
I don't yeah, sorry, I don't know much about multipath phenomenon to comment. Yeah, Gareth, if you heard that.
I missed part of that question. Which figure?
Yeah.
I'm not sure. So it's from John Armstrong. If he wants to say something more, or you guys can talk, maybe he can add more. We can talk more over the break.
Yeah.
I just put it in the question.
Okay, we'll do that then. Yeah, definitely.
Well, thank you all so much. We're going to take a